Welcome, everyone. Thanks for sticking with us. I think this is the next to last session of the entire conference. So thanks for being here. My name is Eric Hand. I'm the European news editor for Science Magazine. In a previous lifetime, I was a physics reporter, and one of my first stories was on ITER. This was over a decade ago. And ITER is still a story, and it still will be for some time. So before we get started, and before I introduce you to Bernard Bigot, the Director General of ITER, we're going to play a short video that ITER has produced that I think will help give you a quick overview of the project and maybe orient you and give you some of the basic terminology and ideas that you're going to need to enjoy our conversation. So if we can bring up the video, please.
Energy is like oxygen for life.
As long as you are a human being on the Earth, we need energy.
The planet is fine, but it will get rid of us.
And so we need innovation.
We have the potential and the capabilities to have cleaner sources of energy and more diverse sources of energy as well.
One of the ways we think is the best way to do it is to actually replicate what happens on the sun.
The principle is quite simple. When you have two atoms of hydrogen, if you make them collide, they will fuse.
When doing so, they liberate a huge amount of energy. The energy we will then use to actually produce electricity. It sounds simple because stars have been burning on fusion for billions of years.
It's the fundamental energy of the universe.
But we need to control it on Earth.
Here we are, it's ITER.
ITER is a large international program in order to demonstrate the feasibility of fusion technologies.
Probably one of the biggest scientific and technological challenges that human race had to face.
In the sun, the pressure is very high.
To get that same kind of collision of nuclei, we need really high temperatures.
150 million degrees in ITER.
It's quite hot.
Probably going to be the hottest point in the universe right here in Cadarache.
You can't really make the same scale of the sun on Earth. We have to use a special device called a tokamak, which is basically like a donut.
So we are now constructing the whole platform and then starting to construct the machine itself before we can actually use it.
Here you have the tokamak.
The plasma is the state of the hydrogen when you heat them and you produce fusion power.
So you can think of a plasma as a ring of lightning, if you wish, which is traveling around the machine, held indexed by strong magnets.
There is many challenging technology to have to be assembled and working all together, and it is a challenge we have to face.
So where I stand, there will be the vacuum vessel, and attached to the vacuum vessel, you will have 440 modules of the blanket covering all the vacuum vessel and facing the plasma, and roughly about 600 meters square in area.
Basically, the main fuel source will be seawater.
This huge machine is fueled by this tiny pellet.
We are now making things which have never been done before.
Just to give you an idea, these neutrons have so much energy, there was nothing to stop them. If it was in space, it will travel from here to the moon in 8 seconds.
There is, I would say, a miracle around ITER.
It's always shown that the planet is able to collaborate on a scale somewhat above the normal argument level.
It's more than 30,000 people all over the world working in order to deliver and manufacture the different components.
Obviously, it's quite a challenge to keep the plasma contained inside a tokamak. So to do that, we need some super strong superconducting magnets.
This is the superconducting cable to be wound in a circle shape.
So the largest magnets that have ever been manufactured in the world.
You need these very large magnetic cages in order to maintain this 150 million degrees plasma away from the wall.
The magnets are super cooled because they have to be really strong. They're one of the coldest things in the universe.
So in 10 meters, you go from nearly absolute zero to 150 million degrees. I can't imagine anywhere in space where you can find this kind of gradient.
As a scientist, I have been looking for this technology for several decades.
Everybody knows what they're doing, they're just going to get on and do it.
If we succeed, it will be a real breakthrough for the energy supply for the world, not just a century, but millions of years.
We really need to work on this as soon as possible and prove this as soon as possible.
The future energy issue will be on our shoulders.
And we don't then prove that fusion is a possibility, then I think that this as an energy source for the future will be lost.
And now we as a team need to prove that we can do what we promise.
A dream is just
getting reality.
If ITER works, you have demonstrated that you can create large amount of power from fusion reaction, and it gives rise to the hope of designing then fusion reactors which can produce electricity in the future.
If we master it in an efficient way, we have no more problem with any energy issue.
Dun, da, da. All right. And look at that. Here we are. Dr. Bigot, can you see us?
Yes, very well.
Hi, great. I'm so glad this works. So I'm Eric Hand with Science Magazine, and everyone, this is Dr. Bernard Bigot. Let me do a quick introduction, and then we'll be on our way. So Dr. Bigot is the Director General of the ITER organization. He was appointed in 2015. Before that, he was the chairman and CEO of the French Alternative Energies and Atomic Energy Commission, or the CEA. It's a government-funded technology research organization with an annual budget of more than 4 billion euros. Before that, from 2003 to 2009, Bigot was France's High Commissioner for Atomic Energy, an independent scientific authority whose mission is to advise the French government and president on nuclear and renewable energy policy. Dr. Bigot was trained at the École Normale Supérieure in St. Cloud, and he holds a PhD in chemistry. He is still a university professor at the École Normale Supérieure in Lyon, which he helped to establish and which he directed from 2000 to 2003. Basically, Dr. Bigot was the world's foremost expert and champion of nuclear fission power before, and now he is the world's expert and champion of nuclear fusion power. So thank you for being with us today. I'm sorry I couldn't be in person, but this actually looks pretty good, and moreover, we get to see the machine itself rising behind you.
Exactly.
Okay.
Thank you to accept this way to have a meeting with you today.
Excellent, excellent. So the way I view this session, I have a long list of questions. We'll see where they take us. I'll probably use about 40 minutes or so, and I'd like to save some time at the end for questions from the audience. I did want to start we have a slide up here, I don't know if you can see it, Dr. Bigot, of the tokamak itself. I just, the numbers rushed by so fast in the video, I just want to kind of marvel at them for a moment. The tokamak itself, 1 million components, 10 million parts. It will weigh 23,000 tons. That's 3 times the weight of the Eiffel Tower. The toroidal magnets, which you can see in orange over there, the D-shaped magnets, 17 meters tall, by the way. They contain 100,000 kilometers of niobium tin wire, enough to wrap around the Earth twice. The center of the tokamak of the plasma will reach 150 million degrees. That's 10 times hotter than the core of the sun. And then just outside the vacuum vessel where the magnets are, which have to be cooled to superconduct, it's going to be about 4 degrees above absolute zero, the cold of space. So, this is the largest scientific collaboration in the world, and you could easily argue that it's the most expensive, most complex engineering project, scientific or otherwise, ever attempted on Earth. So I can't decide if this is a story of, the magnificence of human ingenuity or one of hubris. So I guess my first question for you, Dr. Bigot, is this crazy? Are you crazy for even trying to do this?
I don't feel I am crazy. Feel just I am considering that the world needs some alternative option on the way we are supplying energy to our citizens. I'm sure you understand that the world population has grown up where it is now due to the fact that we have a wealth of energy coming mainly from fossil fuels. It will not last forever, so we need to explore some alternate option. And it's good to see that the physicist has discovered that what powers the universe is just hydrogen fusion. And so why don't we take advantage of this natural phenomena in order to mimic that on Earth and to control it in order to provide enough energy for very long term to the whole mankind. Right. So I am not crazy. Many people which are working for ITER are not crazy. They are just dreaming, to contribute to this project.
As we can see, there's something that's actually real behind you. Maybe you can give us a quick status update. I know you passed, I think it was a 50% milestone a year or two ago. Maybe you can tell us where the construction, the status of the project is right now.
As you imagine, there is many activities which has to be performed before we could have this system working properly. So when we start in 2007, we design the project, and we decide about the procurement of all these components. And maybe you know that indeed the 7 members are considering that fusion could be a real breakthrough, and they want that each of them able to prepare their industrial champion in order to demonstrate they are able to deliver. So it's why we have break down the component and all the need of the different materials within the 7 members. And for that reason, we monitor very carefully the progress of their manufacturing capacity. We have divided indeed the project in nearly 25,000 activities, and each of these activities has been weighed in such a way we could monitor the progress. And we are pleased to say that by November 2017, we passed over the 50%. Now we are nearly 65%, which means that mainly the buildings which will host the tokamak and all the other components are near completion. We expect to have this building ready for equipment by next March 2020. And on the other side, all over the world, in the workshop of the ITER members, we see a lot of progress on the way the components are manufactured. Some of these components, for example, will come on site by next September, some early next year, and we will start the assembling of all these large components around April, May 2020. So we are now passing over, I would say, the breakthrough points where we move from what we call the design and manufacturing to the assembling and installation for finalizing the construction. The next years will be absolutely decisive. We will receive all the components from the world, and we will have to assemble them. And I'm sure everybody understands that it is when you assemble the piece you have been able to manufacture before, you really check if your design, if your mission, if your plan is working.
All these pieces are going to have to fit together to incredible tolerances. So are you still on track for first plasma in 2025?
Exactly, we are on track. When we come in 2015, we have made a thorough review of the project on scope, on schedule, and on cost.
Okay.
And we propose to the ITER members to have a very, I would say, challenging schedule from 2015 up to first plasma by 2025. And after that, we have a stage approach going on, complementing the installation with some of the equipment which will not be ready by 2025 for full fusion power by 2035.
Okay.
And I am pleased to say that despite all the challenges you could imagine when you have so large number of components to manufacturers to properly consider for assembling, we are on track. Every month, now for more than 3 years, we are progressing around 0.7% per month, 0.6, 0.7% per month. And if you consider that up to first plasma 2025 is nearly 80 months, if we keep on this pace, we will be on track.
It's an
It's
immense,
not,
it's an
we have
immense
to be
construction
overconfident.
process. So
Yes.
thank you for that. I want to make sure we cover a lot of ground. I've divided my questions into three areas. I want to come back to the science and technology of the machine, and I really want to talk about kind of fusion as an energy source and in the context of society and economics. But first, actually, I want to talk about the ITER organization itself and its structure and some of the really interesting politics of ITER. So you have 7 ITER partners representing 35 nations. You're almost like a mini United Nations. You had to invent your own unit of currency called an ITER unit of account. And then your hundreds of employees speak dozens of different native languages. And you also have to contend with their different science and engineering cultures, different terms and concepts, metric systems, different cultures for approaching risk and safety. How do you prevent the project from becoming a sort of Tower of Babel?
Clearly, you point out and underline rightly that it is a challenge. What we do is we have defined rules of the way to work together. We have to work as an integrated team. Everybody has to respect some basic, I would say, values, some basic principle in order to work together. Again, it has been well recognized that when I came in, the ITER Organization Director General has to be fully empowered to take any technical decision. If not, okay, the Director General is useless. So it has been a precondition in order to move forward. If the ITER members don't agree that if you delegate the power to the ITER Organization Director General, you have to let him work this way. And if not, okay, it's better that you leave, let him leave immediately. This value is very clear. We want that the people try to demonstrate on a daily basis their professional excellencies. Second, people has to work on full trust. Okay, everybody has to express freely within the project when it is a time for debate and discussion. He has also to consider to work as a teammate, which means that if you face any difficulty, we have to support you in order to fulfill your mission. And maybe the most important is loyalty to the project. What it means, loyalty to the project? Everybody has to consider that any action he has to take is in the main interest of the project. And a very simple illustration is related to decision process. There is a time for discussion, and when it's come to take a decision, the DG or the people he has delegated the power has to take the decision, and even if before people has different views, everybody has to implement the decision. And if people don't do that, it is himself which put aside of the project, and we have to move on without him. So it is on this basis that we have been working since 4 years, and I am pleased to say that we have a very good behavior of all our colleagues coming from the 35 different countries you mentioned.
I still find that amazing. I mean, can you give some examples for good or bad of some of the cultural particularities in the project?
Okay, clearly there is a larger of diversity. But when it comes to take a decision, as I explained to you, the people are free to express their view. They could express their own experience. They could provide any insight they could have. But at the very end, it has been accepted by all that as long as the DG, ITER Organization Director General, is in office, he has the last words. And when a decision is taken, everybody has to implement. I will give you an example. When I came in, it was a long debate, nearly 4 years, where we will position the tokamak cooling water system, the primary circuit which will extract the heat from the tokamak. Some people say it has to be inside what we call the bioshield wall, this large, 30-meter diameter, 30-meter high cylinder of concrete, because it's prevent any radiation outside. And some others said, no, sorry, we have to put it outside of this bioshield wall, because we need to maintain this equipment. We need to preserve the possibility to adapt to this. And it has been going on and on, but I say very clearly, we need to take decision. We have 2 months for debating. Everybody we want to argue has to present, these views, and in 2 months we will take decision. And I am pleased to say that everybody has worked very hard. They have a hot debate, I would say, but at the end of the day, it was quite interesting to balance the pro and the con, and we have taken the decision, and since that, we are really moving forward full speed in order to implement this decision. So it was a critical decision, and everybody has respected the rule.
So it sounds like it's important not only that you're a scientist, but also an excellent diplomat in making these decisions happen. I wanted to point out that it's not just your staff that is an international melange. This machine itself is an international patchwork built from pieces from all over the world. I can give you a few examples if you're looking at the slide here. The vacuum chamber, the vessel that faces the plasma, has 9 different segments. 2 of them were constructed in South Korea, 7 in Europe. These orange toroidal magnets, which confine the plasma, are also divvied up between Europe and Japan. And then the wire that makes those magnets, the 100,000 kilometers of this special superconducting wire, was procured from suppliers in 6 out of ITER's 7 members. It seems like a tough way to build a complex machine that needs to be built to very precise tolerances. Why did you have to do it this way?
Clearly, to be frank with you, it will not be considered as the best way to manage a so large project. You feel that it would be better to have just, for example, a large consortium of suppliers to provide with the same manufacturing strategy, the different components. But it was a prerequisite. The 7 members, all of them think about that fusion power, hydrogen fusion, could be a real breakthrough in the future, and they want to prepare their best industry champion in order to demonstrate their capability. So we had to accept that, but we have also to maybe correct the drawback of such a decision. And the way we decide to do that is to set up what we call project team. What's mean you gather all the different stakeholders in charge of a given component and under the leadership of one single person which has been accepted by all, all are working together and try to work as much as they can in the most coordinated way. So again, I repeat, in the future, I hope we will not repeat this exactly same way to proceed, but it was a precondition. We have to accept this precondition, and I am pleased to say that since I am in office, I have seen very goodwill of all the people overcoming the challenge of having this, as you said, Korean manufacturing some of the sectors of the vacuum vessel, which are very challenging. Could you imagine there are some pieces which are weighing 450 tons, nearly 20 meters high, and we have to have them with a precision of millimeter to fit with the other vacuum vessel sectors and to be properly welded together. Okay. But close quality monitoring and goodwill and teammate spirit help a lot.
I have one more question in this vein before we come back to the machine itself. I was trying to think of other massive, big science projects around the world where power or authority was decentralized, maybe like ITER, and I was thinking maybe of ALMA, which is a giant radio astronomy array in Chile that's split between the US, Europe, and Japan, and it has gone through similar growing pains like ITER, lots of delays, cost rises, and a difficult process of integrating dishes manufactured in different places. And then I was trying to think of other big science organizations like ESO, the European Southern Observatory, or right here in Geneva, CERN, and its Large Hadron Collider, where treaties maybe give the central authority more control. I wonder if, after your 4 years now in charge of ITER, I wonder if you have any general thoughts on the best way to pursue big science, the best way to set up an organization and to find a balance between attracting partners and their money and having enough control to actually make something happen.
As you know, anytime you try to make people working together is a challenge. There is no final recipe. From my point of view, when you have a so large project which needs the support of 35 different countries for nearly 40 years, and waiting maybe 20 years before you see the project operating, you need to be sure that all the stakeholders are aligned with the final purpose, with the final target. And it's why it's worth to take time to explain in detail, what you are expecting to do, what is your roadmap, how the people could monitor your progress. And I guess it is a basis of the long-term trust you need. So it's depending on any project. As I mention very often, not a single country, whatever powerful it could be, could easily deliver the ITER project in a reasonable timeline. Could you consider that 35 different countries representing over 85% of the annual GDP, worldwide annual GDP, will take nearly 25 years to build and start full fusion power. A single country, whatever powerful it could be, it will take a century. So we could not afford. The urgency to demonstrate fusion capacity command that we really work together. So every members, I do believe, are fully aware that there is no alternate option to work like this and accept common rules in order to be successful.
Okay, let's come back to fusion itself and talk a little bit more about the technology of the ITER tokamak. So maybe you can start by explaining to our audience these three concepts or thresholds in fusion energy: gain, burning plasma, and ignition. It seems like different organizations sometimes talk about them in different ways, but how do you explain these three concepts?
Okay, as I explained, fusion is a very usual, largely known phenomena in the star and the sun. In the star and the sun, it's because you have a huge mass, and I'm sure you know that the sun is nearly weighing 300,000 times the weight on Earth, and under what we call gravitational pressure, you force the hydrogen nuclei to get closer and closer, and at a given time when they get so close, they are fusing and they produce two new particles which are expelled with a lot of energy, which is a neutron and an helium nuclei. You could not do that. You could not do with gravitational pressure on Earth. So you need to go really other way, and the way the physicists have considered is to have collision with very high speed in a zone where you have very little neighbor, which means very high vacuum. You could accelerate the hydrogen nuclei in order that when they will collide, they will get so close again that they will fuse with a high efficiency. So the key phenomena we have to control is how we accelerate the particles and such a way they will collide. And the second point is that we need to have, at a given time, sufficient fusion phenomena, fusion events, in such a way it overcomes the energy you have to feed in to accelerate your particles. So the size is a prerequisite in order to have a net outcome of energy, considering the energy you have to feed in order to have this fusion phenomena. So just to make it simple, we have to have a huge vacuum vessel with a very low density. The density will be 1 million the density of the atmosphere. In this condition, there is enough time with the magnetic forces to accelerate the particle before they collide, and when they collide, they will fuse. And due to the size of this tokamak, of this vacuum vessel chamber, you have enough phenomena in order to produce energy. You have to think about that just 1 gram of hydrogen, when they fuse, is like if you burn instantaneously 8 tons of fossil fuels.
So let me try to restate some of this before we get too far along. So I think your first point was that we can never match the incredible pressures of the sun. So instead, here on Earth, we're going to go to extremely high temperatures, higher temperatures than the sun, so that the hydrogen particles are moving so fast that they have more of a chance of fusing. But again, this concept of gain, you are going to be the first machine to extract more energy from the plasma than you put into the plasma. And this has been a threshold that tokamaks around the world have been seeking to break for the last 50 years, yeah?
Absolutely. There is many tokamak indeed which are now operating in the world, but they were all too small in such a way that the volume of the plasma was not appropriate in order to have sufficient fusion event at a given time in order to overcome the energy you have to feed in order to get this very high temperature. The high temperature is 150 million degrees, 10 times the temperature of the core of the sun. Right. So your point is very well done. It's because we need to have a large volume of plasma where fusion could operate, which will be able to yield a large amount of energy, compensating the energy you have to feed in.
And you're planning on not just going past this break-even point or a gain of 10 times, but even further, you're hoping to reach what you call a burning plasma state. Can you explain that concept?
Okay, the burning plasma is the following. When you have a fusion between 2 hydrogen nuclei, you will produce an helium nuclei and a neutrons. The helium nuclei will get out of the fusion with 5 times more energy than the whole energy of the hydrogen when they collide. 5 times more. And the neutron 20 times more. And so, because the plasma is just confined by large magnetic cages, the hydrogen as well as the helium nuclei will be confined. So the helium will stay within the plasma, and it will collide with the hydrogen atom in order to heat them up. And so is why we name them a burning plasma. It means it is a self-sustained plasma, indeed not fully self-sustained. The helium nuclei will only provide around 80% of the energy needed in order to heat up, up to the 150 million degrees, the plasma. And when the helium will be just with the same temperature of the remaining hydrogen plasma, you will suck out the helium in order to recycle the whole process. If you keep on the helium in the plasma, it will poison the plasma and it will stop. So again, the self-sustained plasma, burning plasma, is coming to the fact that we will produce enough helium nuclei per unit time in order to be able to heat up, okay, the hydrogen which will be fed in.
So
it will be the first time that we will have a burning plasma.
So your plan is to do your first very initial plasma experiments in 2025, but the fuel that you would use to achieve this high gain and a burning plasma, deuterium and tritium, two forms of heavy hydrogen, you won't use these DT reactions in your plasma until 2035. Early schedules, I think you were going to go there, just a few years after first plasma. So why now are you going to wait so long to attempt to use DT fuel?
It's a good question again. The first plasma, indeed, will be to check with a fuel made of only standard hydrogen, okay, the standard hydrogen, and it will give us the opportunity to check that all the tokamak is well assembled, the cold aware position. But hydrogen standard one don't produce so much energy. Is the best fuel, the best brand indeed is deuterium and tritium. So once we have the first plasma successful, we need to install some further component. They are needed, and indeed they are quite complex, and the 7 members has not the full resources in order to provide them on the same time we are preparing for the first plasma. What they are, these components? First, they are what we call the first wall, which will collect the neutrons with their 20 times more energy that the hydrogen will collide. It is made of 440 tiles, and it will collect the neutrons, and like a bullet on a silver plate, they will be stopped abruptly, and they will transfer their kinetic energy, their speed indeed, to heat. So this takes time to install. You have to think about that each of these tiles, 440 as I said, with their support, each of them weight 4.5 tons. So we have to install them with robots, with a remote handling system. And so it will take time for that.
I thought it was also because, once you start using tritium, which is radioactive, you have to be very careful. You're not going to be able to go into the machine and tweak it and change it. That once you start using DT fuel, your hands are going to be tied to a certain extent.
You're right also. It's a very good opportunity to check that everything works fine before we start full power with tritium and also with a lot of energy. So it's why we go stepwise. Indeed, the first campaign we will offer to the physicists will start in 2028, where they could start having real physics experiment, a very original one, with deuterium fuels. 2028, we will offer them 18 months to play around with the tokamak and learn how to take full benefit and advantage of this unique capacity. After that, we will have some extra heating to give them more opportunity to explore higher energy scenario. And the very end will be when we will install what you call the tritium plant. We will recycle the tritium. You have to think about that at a given time, you have only 2 grams of fuels in the tokamak. 2 grams in nearly 1,000 cubic meter. High vacuum, as explained. And it's only a few percent, indeed less than 1% of this fuel which will fuse before you need to extract the helium nuclei. And so you have a constant recycling process to deal with. It's quite an advantage, I would say, for these technologies, because if anything goes wrong, you could stop it immediately without any damage. There is no storage of high energy high heat, you could lose the cooling water system. You could lose the power. There is no risk of a runaway of the tokamak system. So it is exactly what you said. We need to go stepwise to learn how to proceed. And when we will deal with tritium, which clearly need to be cautiously managed in order to avoid any damage with this certainly low radioactivity material, but still radioactive, to avoid any difficulties.
So you'll approach this important threshold very cautiously. So yeah, ITER is the biggest game in town when it comes to fusion, but there are dozens of other efforts around the world, public and private, that utilize different approaches. Many, if not most, use magnetic confinement like you, but there's also inertial confinement, basically using lasers to try and ignite pellets of hydrogen at places like the National Ignition Facility in California and the laser megajoule here in France. And within the world of magnetic confinement, there's different shapes besides this donut tokamak shape. There's spherical ones, there's the twisting shapes of things called stellarators. There's one nearby in Germany called the Wendelstein 7X. Dr. Bigot, how do you view all of these other efforts? Are they competitors for you?
No. They are not competitors for me, they are partners. As I'm sure you understand, fusion is quite challenging. So any option which could be explored and which could make it more efficient, which could make it cheaper, which would make it sooner, is very welcome.
What do you think about these two tokamak concepts being pursued? One in the UK by Tokamak Energy, and the other a spin-off from MIT called Commonwealth Fusion Systems. They're taking advantage of even newer superconducting magnets that can go to even higher magnetic fields so that they can build much smaller tokamaks because they think that will ultimately help them be cheaper.
Okay, clearly I agree with these people that the largest superconducting magnetic field you may have, better it is. It will help you to accelerate much more rapidly. But you have to balance everything. If you take advantage of this higher field, you will have also, if, as you mentioned, a smaller size, and if you have a smaller size, you will have a larger energy flux on the materials. And from my point of view, for the time being, we are really limited by these parameters. Could you imagine that in this tokamak, with this size of 20 meters, depending on the magnetic field, because the magnetic field is directly linked to the acceleration space we need in order to have the high temperature, it will be 20 megawatt per square meter. It's more than 5 times what has been achieved so far now. So from my point of view, it's good to have this superconducting material with a more efficient magnetic field, and it could be bring in a tokamak like ITER. But my guess is if you want to take full advantage with a smaller size, we need also to overcome these material issues. Okay. So it's very often a question I am asked. You are building this during 25 years nearly. In the meantime, there will be big progress, and how you could accommodate. My answer is very clear. We are in a learning process. If we are always waiting for the next progress, the next performance, we will never learn. You know, it's like when you move on a trail. It's nice to have a map and to dream about a way to move for faster or more easily, but you will never know what is a trail and you will not be able to optimize. So from my point of view, all these projects are very welcome. I would be so pleased to see them successful in such a way that we have a full optimization. But from my point of view, based on the physics, the best I know, you need to have a well balance between size and magnetic field. And so far, I guess that ITER would be, for the time being, the optimal choice. If tomorrow we have a higher superconducting materials, higher temperature, it will be even better, but it will not change dramatically the need of space and the need of this quite large and high precision requirement which ITER has now.
Okay. We're progressing rapidly here. I want to come to some discussion of fusion as an actual energy source when it actually comes, or if it comes. Cost. Let's just start and jump right to cost. I mean, this is where my bias lies. I'm going to read you something, a quote from the first chairman of the Atomic Energy Commission, Lewis Strauss. In 1954, he predicted that nuclear power would someday make electricity too cheap to meter. 65 years later, we now know that nuclear power is instead too expensive to finance and build. Throwing aside questions of societal acceptance. Nuclear power, fission power, cannot compete with natural gas. It cannot compete with renewables. Do you worry that fusion will face the same problem of being too expensive?
Clearly, our goal is to make fusion economically viable, economically competitive. And once again, now we have some alternate with the fossil fuel. And the basic idea that someday the availability of the fossil fuel will be highly reduced, not speaking about the climate change issues. It will be reduced because it has been accumulated for hundreds of millions of years, and we are now depleting the resources at a much higher speed. So I do believe that we will need a complementary way to produce energy compared to the renewable energies. The renewable energies is just the sun, providing its flux on Earth and taking advantage for the solar panel, for the windmill, for the biomass production, for whatever you want. All of them are coming from the sun flux. And so we will need to compensate with two intrinsic features of the solar power, which is diffuseness and intermediacy. Diffuseness, you need a lot of space. And now many countries are highly urbanized. So you could not have the space nearby available. So if you want to collect the energy far away, you will lose a lot. So from my point of view, we need alternate. And I don't believe that there is no other way now, from the physics point of view, that the fusion energy to cope safely without impact on the climate, with low impact on the environment, and we could expect to be cheap. Right now, the ITER project is expected to cost around 20 billion euro, value 2016. 20 billion is huge, but as I explained to you, we have not taken the most efficient way to perform. With all the 7 members providing each of them their component, we have a huge integration to do. We have a lot of quality control to proceed in many countries. So I expect that the cost will be much more reduced when we will start with a real fusion power plant in the future.
No, of course. I mean, you would never build a working fusion power plant like you've built ITER. But I still, I was just, I'm not an energy expert, but just kind of back of the envelope, I was looking at what it would cost, capital costs, to build power plants from different sources. And, a 1 gigawatt natural gas plant, would cost on the order of $2 billion. Solar and wind are now, roughly on par with that. Nuclear fission $10 billion to build a 1 gigawatt plant. And yes, you know, ITER is upward of 20 billion euros or dollars, and some estimates go even much higher. I just wonder, do you see a path somewhere in the future of reducing the costs of a fusion plant by, you know, more than an order of magnitude?
Yes, really, I see opportunity for that. And it is one of the mission and purpose of the ITER to see what will be the best way to proceed in order to reduce the cost. I want to point out, you speak about the renewable energy, for example. Let's aside the fossil fuel, okay? We are thinking about to replace the fossil fuel. So the comparison is not worth with the fossil fuel. And from my point of view, the cost of the energy coming from the fossil fuel is not, okay, maybe integrating all the real cost on environment impact, on the climate change, okay, impact and so on. The competition for me would be with the renewable, okay? And again, the renewable could contribute, but the renewable could not contribute to 100% of the world energy supply because of this question of intermediacy and diffuseness. You need to have a complementary system which will produce massive, predictable, continuously, or, okay, you could change the rate of production. And we come to the point of the economically competitiveness. There is several studies worldwide which have studied what could be the cost of a nuclear power plant in the future. They are speaking about, with an optimized devices, of costs which are of the order of 80 euro per megawatt. As we know now, okay, the windmill or the solar energy could be maybe in the range of 40, 50 euro per megawatt. But they could not provide all this. They need a backup. So if you add up, okay, both the cost of the renewable energy plus the backup, we match it. We match it. We could match it.
Okay. I want to make sure we save time for questions. I think we have some microphones on each side, do we? I don't see them. We do, okay. So if you have a question, you can start lining up. One last question for you for the moment, Dr. Bigot. You know, there's this trope within the fusion community about fusion always being 30 years away. You know, but I've seen in other interviews you prefer a different aphorism, one from a Russian scientist, Lev Artemovich. Can you tell us that and explain what it means to you?
Okay, these people say that the world will make fusion power available when the world will need fusion power. So from my point of view, I really feel that now we are on track in order to demonstrate the feasibility of fusion. It's for me like a miracle that the 7 members has agreed to join their best effort for nearly 40 years in order to make fusion a reality. And what pleased me, to be frank with you, since I am in office, we have a very challenging, clearly, but clear schedule, and we keep on schedule. Every month, we are looking on progress, and I am pleased to say that for the time being, we are on our roadmap. We are on schedule. So I see no reason why we will not succeed. Now the physics is well established, even there is still some zone for improvement, for optimization. I feel that the physics is quite robust. Now the engineering has demonstrated that we could do it. Okay, I am pleased to say that recently Japan and Korea has shown us that they are able to manufacture the coils. The coils is quite large. Okay, nearly 20 meter long, 10 meter large, and we have to make some casing in order to prevent the superconducting coils to break apart under the huge magnetic forces, and they have to assemble the 2 parts of the casing with a precision which is below 0.2 millimeters, when it is 20 meters long. And I am pleased to say they succeed. First try, first success. So I am confident that there is a lot of room for improvement and performance in order to make fusion a reality during this century.
Okay, thanks. I want to make sure we have time for some questions from the audience. Okay, we do have at least one. If you could state your name and where you're from. I don't think you can see or maybe even hear. I'll make sure I repeat or restate the question to you, Dr. Bigot. So go ahead.
Thank you.
Hi, my name is Alan Boyle. I'm with GeekWire in the United States. And I wanted to ask about, follow up on what Eric was saying about the competitiveness of your approach as opposed to other ventures like the commercial ventures, TAE and General Fusion, for example. And then you also have TerraPower and other people who are doing small-scale fission. And then you also have progress in developing grid-scale batteries. Some people say if we solve the battery problem, then we solve the problem of intermittent renewable power. Is there a possibility that the world will never need the sort of fusion that ITER is trying to develop?
Did you hear
Your
that?
point is
Sounds
very
good.
well done.
Okay.
You know, it would be in science and technology always major breakthrough. And you're right, if we are finding some way to store the energy, the solar energy, in a very cheap condition, safe condition, it could be no need of fusion. But as long as I have not seen this breakthrough, I need to prepare the world in order to face the shortage of fossil fuels and to be able to complement the renewable energy. So I am really pleased to see many try in such a way that if any of them is successful, maybe we will have to consider as a real winner. My experience in the field of energy, you need some quite large mix. You could not rely on just one technology. As long as you have not demonstrated that these technologies is really robust and optimized for all the purpose, you need to accept to explore many more options. And I am pleased to say, as you said, that people are working on several different options for that. Now,
If I could follow up on that, I mean, I think everyone would agree that it doesn't make sense to put all of your eggs in one basket, so to speak. But you know, ITER is drawing most of the world's capital and expertise for fusion. Your predecessor, Motojima, told Nature in an interview a few years ago that each country cannot contribute to the next stage of fusion with only 50 people working on it. So to concentrate too much on ITER is dangerous. I say that even as its director general. Is there a danger of ITER sucking the air out of the room for these alternative approaches that Alan mentioned?
It's very clear. I don't want to prevent any other option to be developed. Very often when I am questioned by some lawmakers, what do you think about this domestic program we are considering? I say, please maintain your domestic program. As long as we have not been successful, we need to have people exploring and train in fusion. It will be dangerous from my point of view to say, no, just look at ITER and it will be the final word. It's a unique option. Nobody will have 800 cubic meter of plasma. We will offer a unique opportunity for the physicists to explore this very hot plasma, and there is a lot to learn. So in any case, we will learn a lot with the fusion power. And please don't stop any other option. They are needed, they could be complementary, they could maybe bring a lot of added value, including to ITER when we will have demonstrated that ITER will working properly. It could be improving the superconducting material, improving the way we will control the plasma, about the diagnostics. there is many.
Okay.
One I
want to get to some more questions, but before we're running out of time. Some people have just lined up. If I can interrupt, I think David was here first, so go ahead and introduce yourself.
Hi, David Harris, freelance from Australia. ITER is a large machine. It generates a lot of power. But there are many reasons, valid reasons, that we might want smaller machines more distributed around around space, around territory, around countries. If ITER works as anticipated, will the technology scale to these smaller machines?
Did you hear that?
This is the last question, the last one.
Will what you learn at ITER scale to these smaller machines? Can you apply the lessons of ITER to compact configurations?
Okay, again, what we need to do is to create sufficient pressure in order to make hydrogen fusing. I am sure you understand 2 nuclei, which are both electrical positive particles, repel a lot. And so you have to overcome this huge repulsion. And to do that, there is no other way but to develop larger forces in order to overcome that. So, from my point of view, you could reduce the size of a fusion power, but not so much as long as we will work with the magnetic confinement. You need to have enough space in order to accelerate the hydrogen nuclei in order to be able to make them colliding with high efficiency. Again, when we see some alternate option as this system with a huge piston which are pushing the plasma in order to make them very dense, they have to develop a lot of energy also, and I don't believe it will be possible to have a massive production of fusion power if we reduce the size much below this 20 meter we are now. As I explained previously, if you increase the magnetic field capacity, clearly you could reduce the size for the space for acceleration. But in this condition, you will increase the energy flux on the materials. And so you will come to the issues how you could have materials sustaining not 20 megawatt per square meter, but for example, 100 megawatt per square meter. So far, nobody knows how you could sustain so huge energy flux. So from my point of view, there is little chance that we have a small scale fusion power plant in the future.
So unlike nuclear fission, which can be very compact on a boat or a submarine, fusion might always be big.
Yes. It's for me the precondition which comes from the physics, not from the dream of the engineer, not from the dream of the economics. It's come from the physics.
We have a few more questions. Go ahead.
Hello, Dr. Bigot, Dominique Leglu from La Recherche and Sciences et Avenir. The thing you just mentioned are exactly in the lead of the question I wanted to ask you. It's about what's been said and repeated about the erosion of the materials which have to face these very high energy neutrons. So there was a say of niobium not being a right material to be used. So can you explain to us what has happened and which new solution were adopted, if any, for these materials, for these shields against neutrons? Thank you.
Okay, so again, you have to consider the basic and fundamental feature of the different materials. And could you imagine that, for example, the ITER material will work maybe 25% of the time? But when we will have a real nuclear fusion power, fusion nuclear powers, you will work 7,000 hours per year at minimum. So you need not only you need to have a material which is able to sustain high flux, but also which sustain long time for before any replacement. All this challenge has to be explored, and it is part of the role of the ITER project to test and check some new material which will be performing better, maybe to be cheaper than the one we use, and without inducing any radioactivity when they are heated by the neutrons. It is part of the challenge we are addressing with the ITER project.
So these materials need to be tested, or they need to be invented?
They need to be invented. Some of them already exist. We know their performance, but if we want to really optimize the whole process, some of them has to be invented, as you say. We have some option. I'm sure you are aware of this new steel, I would say, where you reinforce a lot their capacity when you distribute within the steel very small oxide, nanoparticles of oxide, which improve a lot their resistance and performance. This has to be tested. And so far now in the world, there is no way to test, because nowhere in the world you have a so large flux of energy as it would be in the ITER project.
Right.
You have never in the world to have a sustained power of several tenths of megawatt per square meter. So again, this facility will allow us to explore many new, I would say, frontiers of material technology and science.
Great. I think we have just enough time if you have a quick question.
Okay, my name is Julia. I'm a science journalist from Russia. I would like to know, how did you find out that this volume will be enough, and why are you not sure that all this stuff will work? Thank you.
Sorry, how did you know that this volume would be enough, and
why are you not sure that everything will work?
And why are you not sure that everything will work?
You know, I am a researcher. I am a scientist. You know, you have to be ambitious, but you have also to be humble. You have to know that any experiment will surprise you. My guess, my expectation, my dream indeed, that we do the best we can in order it will work. It will work, and it will offer, I am sure, some surprise, working maybe better than we expect, working maybe differently than we expect. But I am quite confident, based on the past experience. Many tokamak has been working smaller size, but quite well. And I am quite confident that if we perform correctly with all the best experts in the world, we will fulfill the expectation of the ITER members, make fusion a reality.
Great. Well, Dr. Bigot, thank you so much for joining us today. If we could give him a round of applause. Good luck.
Okay. Thank you, and I welcome you anytime when you want to see on the ITER side that things are really moving forward.